the first evening of these 3 evenings on particles, atoms, and purpose. The structure of the 3 evenings is as follows. This evening we're primarily talking about what's called the standard model of particle physics. And there are a whole series of unexplained fine-tunings that are necessary for life. Next week we'll be talking about not so much particle physics but cosmology, the history of the universe, and the way there also seems to be a series of fine-tunings, unexplained coincidences which are necessary for life. And then finally, in the third evening, we'll consider all sorts of wild things like string theory, the multiverse design, and where God fits into all this. General plan is that I will aim to talk for 45 minutes. We'll then break for refreshments, but rather than having an extended refreshment period, can you bring your coffee back and we'll go straight into discussion. Obviously, some people will leave at that point, but we'll sort of have an informal discussion over coffee rather than an extended discussion break after coffee. I am not aiming at scientists or experts, and although I am a physicist, I am not an expert in this field. I'm an amateur in this field, but I'm interested, and I want to pass on what I think I found out as a scientist and as a Christian. Science is often seen as a challenge to Christian faith, and it certainly is true that there are a series of scientific findings which are difficult to reconcile with Christian belief. But really the theme of these 3 evenings are things which rather strengthen faith, scientific results that are rather compatible with Christian belief and doctrine. Let me start with 3 quotations, and these are all from non-Christians. Freeman Dyson. We actually had Freeman Dyson for a meal in Aberdeen not long ago when he was giving the Gifford lectures, and very, very impressive man, came round for a meal with us. He probably should have got a Nobel Prize. He was is still a very great physicist. And he wrote this. He said, as we look out into the universe and identify the many accidents of physics and astronomy that have worked together for our benefit, it almost seems as if the universe must in some sense have known we were coming. Accidents of physics and astronomy necessary for our existence. Fred Hoyle was definitely an atheist. Freeman Dyson, not a Christian, but not particularly anti. But Fred Hoyle, clearly an atheist, and yet he wrote this: I do not believe that any scientist who examined the evidence would fail to draw the inference that the laws of nuclear physics have been deliberately designed with regard to the consequences they produce inside the stars. So, a much more narrow field, nuclear physics and stars, but a very clear testimony, if you like, from an atheist that there's something funny going on here. Leonard Susskind is almost the Richard Dawkins of physics. He is a crusading atheist, a very, very intelligent man, one of the fathers of string theory. But in his very interesting book on this sort of area, he says this: the real mystery raised by modern cosmology, and here he's focusing more on the history of the universe, concerns a silent elephant in the room. An elephant, I might add, that has been a huge embarrassment to physicists. Why is it that the universe has all the appearances of having been specially designed just so that life forms like us can exist? And of course it's embarrassing if you're an atheist. So, the focus for this evening is on what is called the standard model of particle physics. It really aims to answer this question: what is the world made of? How does it work? But answering it at the most fundamental level. So putting it in a different way, what are the most basic components of the universe and what are the laws that control them? So the standard model is an attempt to answer that question. Don't panic, we're going to come back to this later on. But there is a quick overview of the standard model, and that's where we're aiming tonight. Rush on quickly. The first thing to say, if we ask what's the world made of, is this: everything is made of atoms. Stephen Hawking says, I think correctly, that the greatest scientific discovery of the last 500 years is that the world is made of atoms. Atoms of carbon, atoms of hydrogen, atoms of oxygen, and so on and so forth. A relatively small number of different kinds of atoms. And all the fascinating things that happen in chemistry and biology and whatnot are due to the rearrangement of atoms. Now, the word atom means something that cannot be cut. So the general idea was little things, little balls that couldn't be broken, but you could rearrange them to make things like water. So chemistry really is all about the rearrangement of these indivisible atoms. Worth saying that one reason why it took a long time to establish that atoms are real is that they're very, very small, far too small to see. A nanometer, well, there are 1 million nanometers in a millimeter. There are 1,000 million nanometers in a meter, and an atom is typically a fraction of a nanometer. Okay, so atoms are very, very small. Everything's made of atoms. What are atoms made of? Well, we now know the structure of an atom. An atom has a nucleus in the middle, surrounded by electrons. The nucleus is electrically charged positively. The electrons are negatively charged. So, carbon, for example. Carbon has a charge of +6 on the nucleus, and it's surrounded by 6 electrons, which are negative, so that makes it neutral. And the negative electrons are attracted by the positive charge in the middle, and it's an electrical force that holds the atom together. Now, intriguing thing is, atoms are small. The nucleus is very small. About 30,000 times smaller than the atom. But, although it's so small, it contains virtually all the mass, the weight, the stuff of the atom. More than 99.9% of the mass or the weight of the atom is in the nucleus, even though it's so very, very tiny. Here is a sort of a picture of a carbon atom, and you see 6 electrons going round, 2 of them in the middle and 4 going round outside, and in the middle this nucleus. So the carbon atom has a diameter of about 0.15 nanometers. You need 6,000 million of them in a row to make 1 meter, so they're very, very small. A femtometer, well, there are 1 million femtometers in a nanometer. Okay? And the carbon nucleus has a diameter of about 5 femtometers. So again, about 30,000. That nucleus on that diagram is much, much bigger than the actual nucleus, which is too small to show on this diagram. You need 30,000 to stretch to make a line across the atom. And most of science is actually to do with nuclei of the different elements surrounded by electrons. Sometimes the nuclei form metals or crystals or whatever, but it's electrons moving around nuclei in response to nuclear forces, which explains almost everything. The calculations are complicated. It uses something called quantum mechanics, which is subtle and difficult, but it's understood. So proteins and DNA and semiconductors and diamonds and glass and all the other things that make life and the world so interesting are explainable in terms of nuclei and electrons acting with electrical forces, plus, of course, gravity. So the next question is, well, what are electrons and nuclei made of? If the atom is made of electrons and a nucleus. For those of us in the West Church, the next stage is called going deeper. That's an in-joke, sorry. What are electrons made of? Well, so far as we know, with the electron, we've come to the end of the road. Electrons aren't made of anything else. They are simply little points of charge. Experimentally, this has been proved to about 1,000 times smaller than the diameter of the nucleus. You fire electrons hard at each other and they seem to behave like point charges down to that size. So far as we know, electrons aren't made of anything else. They are fundamental. But we'll return to that in talk 3. So electrons are just electrons. They're fundamental. What's a nucleus made of? Well, a nucleus has got a structure. It has got components. A nucleus is made of protons and neutrons. The protons are positively charged, charge of +1. the neutrons aren't charged, they're neutral. They both have about the same mass, it's called the atomic mass unit. So, carbon, 6 protons, 6 neutrons, it's got a charge of 6 but a mass of 12, and it's surrounded by 6 electrons to make it neutral. Now, if the nucleus is made of protons and neutrons, what holds that together? It's not electricity, because the protons are positive and they blow each other apart. A positive charge repels another positive charge. So it ain't electricity which holds the nucleus together, there's something else which binds the protons and the neutrons together to make a nucleus. Just to focus this again, here's the carbon atom. It's got electrons going around in a complicated structure outside, neutrons and protons in the middle, 6 neutrons and 6 protons, and they're held together by some very, very strong force. This is maybe a bit small to see, but this is information about the nuclei. The nucleus is of different elements. So, look in the middle here to carbon. That's the nucleus of the carbon atom. It's got 6 protons, 6 neutrons, mass of 12. But you can also have carbon-13, which has got 6 protons and 7 neutrons. It's still got 6 electrons, so it's still carbon, electrically and chemically, but it's got 1 more neutron. But you add 1 more neutron, you get carbon-14. That's painted green, because carbon-14 isn't stable. Leave it for about 5,000 years and it falls apart. All these green ones here are unstable. All the yellow ones are stable. But you see the point, you can have different numbers of protons going with the same neutron. It's still the same element, but it's got quite a slightly different mass. Okay? Now, this is an introduction to the area of nuclear physics. I said most of science is nuclei and electrons. But there's a lot of nuclear physics. If you want to make nuclear reactors, that's a change of the nucleus. Make a nuclear bomb. Understand how the inside of stars work. Nuclear medicine, both diagnosis and treatment, involves the nucleus and changes in the nucleus. Or radioactive dating, a hugely important area which involves nuclei which are unstable. So, the nucleus is made of protons and neutrons. Now the question is, what are protons and neutrons made of?